So in this video, we are going to return to a previous topic, which is how neurotransmitters are released and how they are received and what happens to them. So we've covered how they're released in LO10. So now we are going to talk about how the signals stop getting received. And there are three different ways. All right, let's go ahead and dive in. Okay. So we're talking about this step 4 here. Neurotransmitter signaling is ended by degradation or reuptake. How does that happen? So depending on the neurotransmitter, there are basically three ways in which that happens. The first one is diffusion away from the synapse. So they're put into the synaptic cleft. Some of it just diffuses away and then it's not there anymore. Okay. The other two are things that happen with the neurons or around the neurons themselves. This one depends on the neurotransmitter. So depending on the neurotransmitter, you either get reuptake into the presynaptic terminal, and that can happen either with neurons directly into the presynaptic terminal or by astrocytes, the glia, the astrocytes, they reuptake them and they give it back to the neuron. So that entails having a transporter, and that transporter takes it out of the cleft and back in. Or you can have enzymatic degradation. So there usually are, for these other neurotransmitters, there are enzymes that hang out in the cleft or sometimes on the extracellular side of the membranes, and they will go and chop up the neurotransmitter. Sometimes you uptake the pieces and reuse them, and sometimes you just let it go. And then finally, a final mechanism is receptor desensitization. This is true of all neurotransmitter receptors. They have the ability to desensitize, and that also stops signaling. And I'll talk more about that. Okay. Question for you. Acetylcholine is a neurotransmitter that's used at the neuromuscular junction, which is the synapse between the nerve and the muscle. Sarin nerve gas inhibits the enzyme that breaks it down, acetylcholinesterase. What happens when you apply sarin to the neuromuscular junction? Go ahead and think about that. Okay, let's think about this. Acetylcholinesterase breaks the acetylcholine down. Okay, so acetylcholinesterase takes acetylcholine essentially away from the synaptic cleft. If you inhibit the enzyme that breaks it down, that means the enzyme won't work and there will be more acetylcholine. Okay, so we're down to C and D now. Well, if the acetylcholine is in the synaptic cleft, it will activate the AChRs, that stands for acetylcholine receptors. It will activate those, and that will cause too much muscle contraction. And so that is C here. And why does that cause paralysis? Because that's, what happens when somebody is exposed to sarin nerve gas. It turns out when your muscles are stuck contracting, your muscles are paralyzed. Sarin gas victims, they can't breathe because their diaphragm muscles are paralyzed. And so unless you give them respiratory support, they will die. Okay. The last way is receptor desensitization. So the previous two ways, diffusion and either enzymatic breakdown or reuptake, they take the neurotransmitter away from the synaptic cleft. Receptor desensitization is different because the neurotransmitter is still in the synaptic cleft, but the receptor stops responding to it. So if you recall earlier, right, voltage-gated sodium channels inactivate. In other words, they stop passing current even though the voltage is still depolarized and the channel should still be open. Very similarly, neurotransmitter receptors can desensitize. That means they stop passing current even though the neurotransmitter is still present in the cleft. And so similarly to the voltage-gated sodium channel, which inactivates, neurotransmitter receptors have kind of three different states or three different ways they can be. One is closed, right? So there's no current through them, and there's no neurotransmitter around, and that's why they're closed. When the neurotransmitter is present, that will bind to the receptor, and the receptor will open and will pass current or will do its thing. After time and neurotransmitter, they get into a desensitized state. Now, different receptors desensitize in different ways. Some receptors, tending to be the ionotropic receptors, they desensitize by the channel changing state, so that they're still there. The neurotransmitter is still there, but no current passes through. Many metabotropic receptors, on the other hand, they desensitize because the body simply removes them from the membrane, so they're not there. The neurotransmitter is there, but the body has removed these receptors from the membrane, so the receptor is not there. And obviously, if the receptor is not there, it is not going to cause any effects. Okay. And then after a while, after the neurotransmitter goes away, it can go back to normal with the channels simply being closed, or the channels being in the closed state restored to the membrane. But big idea here, desensitization is another way to end signaling, um, um, because the neurotransmitter is there, but you get less of a response or no response from the receptor. Okay, question for you. A researcher found a mutation in a receptor for the neurotransmitter glutamate. The mutant receptor does not desensitize. How will that affect the receptor signaling? What do you think? Okay, so here you will get more glutamate receptor signaling. Why? Because desensitization reduces receptor activity. So if you block desensitization, the receptor activity will not reduce, and therefore overall it will increase. All right, I hope that makes sense. These mechanisms are all super important, as you can see with the sarin nerve gas example, right? If we didn't have enough acetylcholine signaling, we wouldn't have any muscle contraction at all, and we would die. But on the other hand, if you have too much um, signaling, right, then the neuron is or the muscle is contracting and contracting, and that is also bad, because that can also cause paralysis. And we know this from neurons as well, right? When neurons don't signal, that can cause problems. They're not active enough, or when they're too active, it can cause maladies like epilepsy. So you need the neurotransmitter there, but you also need to remove it from the synaptic cleft or change your response to it appropriately so that you don't have too much signaling. Okay, thanks so much. See you next time.